Vector database simplified. So a vector database is a type of database that stores and manages data in the form of vectors. In mathematics, a vector is a quantity that has both magnitude and direction. In the context of vector database, each record or piece of data is represented as a vector, which can be thought of as a point in multi-dimensional space. So this vector database is designed to handle large amount of data that can be represented as vector, such as image and text data. And it can perform operations on these vectors to support tasks like similarity search, clustering, and classification. So this type of database is particularly useful in applications such as search engines, recommender system, and machine learning. The key components of vector database. So the key components of vector database are data structure and algorithms which are used to store, manage and manipulate these high dimensional vectors that represent the data, and some of the components include vector storage. So the vector database stores the vectors in a way that allows for efficient retrieval and manipulation. This can be done using specialized data structure such as hash table, trees or graphs, which are optimized for high dimensional data. Then comes similarity matrix. So this vector database uses a similarity matrix to compare the similarity between vectors. And the popular similarity metrics include cosine similarity, Euclidean distance, and Jacob similarity. Third comes the indexing. So these vector databases often use indexing techniques to speed up search and retrieval operations. And this indexing allows the database to quickly locate and retrieve the vectors that are most similar to a query. Then comes search algorithms. So these vector databases use specialized search algorithms to efficiently search for vectors that are similar to query. And these algorithms can be based on techniques such as brute force search, k nearest neighbors, or locality sensitive hashing. Then machine learning algorithms. So these vector databases can also use machine learning algorithms to perform tasks such as clustering, dimensionality reduction, and anomaly detection on the data. Then comes query language. So many vector databases provide a query language that allows user to perform complex operations on the data, such as search clustering and classification. Finally, APIs. So many vector databases provide APIs that allow developers to integrate vector database into their applications, making it easier to use vector database in a variety of settings. Then how does this vector database work? So this vector database works by representing each piece of data, such as a document, image or product, as a vector in multi-dimensional space. And each dimension in the vector represents a feature or characteristic of the data, such as a word in a document, a color in an image, or a price of a product. Now this database stores these vectors along with their associated metadata, such as the ID or the name of the document, image or product, in a way that allows for efficient retrieval and manipulation of the data. And this can be done using specialized data structures and algorithms that are optimized for working with high dimensional vectors. So when a user performs a search or a query, the vector database can quickly retrieve and compare the vectors that are most similar to the query based on their similarity metrics, such as cosine similarity used in the database, which allows for fast and efficient search and retrieval of data, making vector database useful in applications such as image and text search, recommender system, and machine learning. Now to visualize all these things, we will calculate the vector database by hand. So here we are given a data set of 3 sentences. Each has 3 words or tokens. So in practice, a data set may contain billions or millions of sentences. and the maximum number of tokens may be tens of thousands. For example, in the Mistral 7B, that was 32,768. So here we will process how are you, and it will check the other things. So first we are given a word embeddings. So for each word we will look up for the corresponding word embedding from the table of 22 vectors, where 22 is the vocabulary size. In practice, this vocabulary size can be tens of thousands. So the word embedding dimensions are of thousands. Example 10244096. Then comes the encoding. So we will feed the sequence of word embeddings to an encoder to obtain a sequence of feature vector, one per word. So here encoder is simple one layer perceptron, that is having a linear and ReLU layer. So in practice, the encoder is a transformer or one of its many variants. Then comes the mean pulling. So here we will merge the sequence of feature vectors into a single vector using mean pulling, which is to average across all the columns. And the result is a single vector. We often call it as a text embedding or sentence embeddings. So other pulling techniques are also possible, such as CLS, but mean pulling is the most common. Then comes the indexing. So here we will reduce the dimension of data embedding vector by a projection matrix, and the reduction rate is 50%. In practice, the values in this projection matrix is much more random, and the purpose is similar to that of hashing, which is to obtain a short representation to allow faster comparison and retrieval, and the resulting dimension reduced index vector is stored in a vector storage. Next we will process who are you. So here we will repeat these steps. We have indexed our data, and then we will check am I you. So here also we will repeat all the steps, and we will do the dot products between the query vector and this database vector, and they all are 2D. The purpose is to use dot product to estimate the similarity. So by transposing the query vector, this step becomes matrix multiplications. And in the last step, we will have a nearest neighbor. That is, we will find the largest dot product by linear scan. So the sentence with the highest dot product is who am I? In practice, because scanning billions of vectors is slow, we use approximate nearest neighbor algorithms like hierarchical navigable small words. So let's understand this thing, right? So here we are given this database. How are you? So we'll check. It is one. How? We will take this purge. How are you? Right? So here we have taken 101 like this, 1010 0110 and like this. So next sentence is who are you? So we'll search where it is written who are you. So we will just copy these things, who, then we will search where are is written. So this way, right? Next, who am I? So here we will check who am I. So we will write the corresponding vectors terms here. So here we will write am I you. So we'll check where am is written. So we'll take its elements and paste it here. Then comes the encoder. So in encoder we will use our popular formula, that is y is equals to wx plus b. We know w is the weight, b is the bias, x is your input matrix, right? So we will use that popular formula here. Okay, so here we know the number of columns are 5. Here number of rows are 4. So we will consider the last one as a bias here. So multiply 1100 with 1010, adding 0 here, we'll get 1 here. Then we will multiply 1100 with 0110, adding 0 bias here, we'll get 1 here. Similarly, we'll multiply this much. So we'll have a dot products like this, and use this formula w y is equals to wx plus b. So similarly we'll do it with other metrics. So here also we'll consider last one as a bias. So here multiply 1100 with 1000, right? So 1 will be multiplied with 1, adding 1 into 0 plus 0 into 0 plus 0 into 0 plus 0. So we'll get 1 here. So then multiply these matrices, then multiply these matrices and get the results like this, right? Then we'll have a mean pulling. Mean pulling means just add these elements and divide by 3. So here 1 plus 1 plus 1, it's 3, so 3 by 3. So here 1 plus 1, 2, so 2 by 3. Here we know ReLU, in the ReLU negative terms are considered as 0, so minus 1 will be 0 here. So 1 only, so 1 by 3. Here all this will be 0 because they are negative terms, so here it shall be 1 by 3. So here also just add these elements this way, okay, and then divided by 3 here. Next we will do we will use the formula y is equals to wx plus b. So here the number of columns are 4, here the number of rows are 4. So simply do the element wise multiplication. So 1100, multiply it with this terms and we'll get 5 by 3. Then again we will multiply this with this and we'll get 2 by 3 here. So again we'll do the same for this one. Then for this one we'll get this. Then when we will multiply this with this, we'll get 8 by 3. Now we will have a dot product here. Right, here we have got this much. So here we are checking this similarities. Okay, so here we will multiply these elements, like we will multiply 8 5s are 40. We'll multiply 2 plus 2 into 2 4. So it shall be 44 by 9 here. Right, so we'll multiply 5 and 8. 8 5s are 40 and 0 into 2. So 40 by 9 here. Then we'll multiply this 8 7 the 56 plus 2 into 2 4. 60 by 9 here. Right, now check the one having the highest value. So it is having the highest value. So we will consider that this is the next word. This is the word we were looking for. And what is this word? That is who am I. So this is how this vector databases are calculated by hand. Next comes the application of vector database. So these vector databases have a wide range of application in various fields, including search engine, recommendation system, machine learning, and data analytics. And some of these main applications include image and search data. So in the image and search data, this vector databases can be used to efficiently search and retrieve images and text documents based on their semantic similarity. For example, a vector database can be used to search for images of similar products or documents containing similar text. The next comes the recommendation system. So this vector databases can be used to store and manage user profiles, item profiles, and user item interactions, which can be used to make personalized recommendations to users. For example, a vector database can be used to recommend movies, books, or products based on the user's past interaction and preferences. Then comes machine learning. So these vector databases can be used to store and manage large amounts of high dimensional data generated by machine learning algorithms. For example, a vector database can be used to store and manage large amount of image data that can be used to train a machine learning model for image recognition. Then comes the data analytics. So this vector database can be used to perform complex data analytics on high dimensional data. For example, a vector database can be used to perform clustering analysis, dimensionality reduction, and anomaly detection on a large set of data. And finally, it's natural language processing. So this vector database can be used to store and manage large amount of text data, which can be used for various NLP tasks, such as sentiment analysis, topic modeling, and name entity recognition. So these are just a few examples of many applications of vector databases, as they provide a powerful and efficient way to handle high dimensional data and perform complex operations on it. Thank you.